source. In the absence of modern batteries or electricity, you might need to harness mechanical power, such as a large spring or a series of gears and levers, possibly powered by water or wind. Structural materials. Wood and metal would be your primary building materials. Iron and steel could be used for constructing a sturdy frame, while wood could provide the base and support structures. Navigational tools. Compasses and astrolabes, which were available during those times, could serve as your instruments for navigation through time and space. Optical components. For any visual displays or intricate optical needs, you might repurpose lenses from telescopes or magnifying glasses, which were in use during those periods. Adhesives and sealants. Natural resins, beeswax, and tar could be used to seal and bind components together. Timekeeping mechanism, a finely crafted clockwork mechanism, which was a pinnacle of technology, especially in the 1400s, could be essential for timing the operations of your machine. Documentation. Parchment, quill, and ink would be necessary for documenting your designs and calculations, as paper was a common material. Embarking on a hypothetical journey to build a time machine in the 1400s, we would need to draw upon the era's understanding of mathematics and physics, while creatively integrating principles of modern quantum mechanics. Here's how we might approach this imaginative endeavor. Mathematics of the 1400s. The mathematical knowledge during the 1400s was primarily based on the works of ancient Greek mathematicians like Euclid and Ptolemy. Algebra was just beginning to be understood in Europe, thanks to translations of Arabic texts. You would need to master these. The physics, mathematics, and quantum mechanics of a hypothetical time machine are deeply rooted in complex theories that push the boundaries of our understanding. Let's delve into some of these concepts. Physics. The concept of time travel is close. Certainly. Let's explore the advanced details of the mathematical equations, physics symbols, and quantum mechanics concepts that would be involved in the theoretical construction of a time machine. Einstein's field equations. At the heart of general relativity, which would govern the curvature of space-time around a time machine, are Einstein's field equations. Here, g_mu is the Einstein tensor representing the curvature of space-time, and t_mu is the energy momentum tensor representing the density and flux of energy and momentum in space-time. Kerr metric, 4 rotating black holes which could theoretically create closed time-like curves allowing for time travel, the Kerr metric is used. Where \delta equals r squared 2 gmr plus a squared and \rho caret 2 equals r squared plus a caret 2 \cos caret 2 \theta. M is the mass of the black hole, A is the angular momentum per unit mass, and r and \theta are coordinates. Quantum mechanics and closed time-like curves. CTC's quantum mechanics introduces the concept of closed time-like curves, which allow particles to interact with their past selves. The density matrix in the presence of CTCs is described by where U is the unitary operator that describes the evolution of the quantum state, \rho_ in U is the initial state, and \rho_ CTC is the state on the CTC. Wormholes and exotic matter. The traversal of wormholes, hypothetical bridges connecting different points in spacetime, would require exotic matter with negative energy density. The Morris-Thorne metric for a spherically symmetric wormhole is where \phi_r is the redshift function and br is the shape function. Energy requirements. The energy required for creating such spacetime structures is immense, often involving quantities like the Planck energy, which is on the order of 10^19 eV, far beyond our current capabilities. These equations and concepts represent some of the most advanced and speculative ideas in theoretical physics. They are the foundation of our current understanding of how time The creation of exotic matter is a topic that sits at the cutting edge of theoretical physics, and it involves concepts that are not yet fully understood or realized. However, let's explore the theoretical pathways and the mathematical concepts that might lead to the creation of exotic matter. Negative mass and energy. One form of exotic matter is theorized to have negative mass and energy. The concept is mathematically consistent and does not violate conservation laws. It could be used in speculative theories like the construction of artificial wormholes and the Alcubierre drive. Casimir effect. In quantum field theory, the Casimir effect can create a region of pseudo-negative pressure density. This is the closest known phenomenon that resembles the properties of exotic matter. High-pressure materials. At high pressures, materials can transform into states that are not typically encountered, such as sodium chloride transforming into compounds like Na3Cl or NaCl3. These materials are stable at high pressures and could exist naturally in environments like deep oceans or planetary cores. Tachyons. Hypothetical particles called tachyons have a complex rest mass and would always travel faster than light. If they existed, they could theoretically be used for communication backward in time. Topology and quantum states. The Nobel Prize in Physics 2016 was awarded for theoretical discoveries of topological phase transitions and topological phases of matter. Using topology, a branch of mathematics, researchers have studied unusual phases of matter, such as superconductors and superfluids, which could be considered exotic states of matter. Wormholes and exotic matter. Theoretical models of wormholes suggest that they would require exotic matter with negative energy density to stabilize and prevent collapse. This exotic matter would repel gravity instead of attracting it, which is a property opposite to that of normal matter. Mathematical symbols and concepts. The mathematics involved in these theories often use tensors and complex geometry. For example, the Einstein field equations g_mu equals 8 pi gt mu describe the curvature of spacetime, and the energy momentum tensor t mu represents the density and flux of energy and momentum in spacetime. These equations are central to the understanding of general relativity and the behavior of exotic matter. In summary, while we have theoretical pathways and mathematical Let's embark on a mystical journey through the realms of theoretical physics and alchemy, where we'll explore the enigmatic world of tachyons, exotic matter, and the fabric of the cosmos itself. Imagine donning the robe of an ancient alchemist with a dash of mad scientist flair as we delve into these arcane concepts. Tachyons, these are hypothetical particles that gallop faster than light itself. In the mathematical tapestry of physics, they are represented by an equation that defies our usual understanding. Here, E is the energy, m is the mass, v is the velocity of the tachyon, and c is the speed of light. For tachyons, the square root becomes imaginary because their speed exceeds c, leading to an imaginary mass. It's like trying to catch a shadow that moves faster than the person casting it. Exotic matter interaction. If you, as an alchemist, stumbled upon exotic matter, it would be like finding a reverse magnet. Instead of pulling things in, it might push them away due to its repulsive gravitational effects. This is because exotic matter is theorized to have negative energy density. Imagine a stream of water flowing uphill instead of down. That's the kind of oddity we're talking about with exotic matter. Topology of quantum states. The universe at its core is a cosmic dance of particles, and topology is the study of how these particles can twist and turn without breaking apart. It's like a pretzel, maintaining its shape no matter how you bend it. Quantum states can be knotted in complex ways, creating stability in the chaos of the quantum world. High-pressure materials. Under the immense pressure of the Earth or the crushing depths of the ocean, materials behave strangely, forming new, bizarre structures. It's like squeezing a sponge and watching it change shape, except at a molecular level. Casimir effect. This is a magical force that arises from the vacuum of space itself. When two mirrors face each other in a vacuum, they are pushed together by the energy of the empty space between them. The formula for this force is where F is the force, h is Planck's constant, c is the speed of light, L is the distance between the plates, and A is the area of the plates. It's as if the nothingness between the mirrors whispers secrets that draw them closer. Remember, these are but the musings of a mad scientist. To step into the shoes of an ancient alchemist, surrounded by the arcane and the esoteric, with the goal of conjuring exotic matter. Let's weave a tale of speculative alchemy using every material, crystal, and compound at our disposal. In our grand laboratory, where the walls are lined with jars of mysterious powders and the air is thick with the scent of molten metals, we begin our quest for exotic matter. Here's how we might proceed. Philosopher's Stone. Our first endeavor would be the legendary Philosopher's Stone, believed to transmute base metals into gold. While this elusive substance is a myth, we'd search for a material that defies the laws of classical chemistry, perhaps a compound that exhibits the properties of negative mass or energy. Crystals and ley lines. We'd align crystals along the mythical ley lines of the Earth, harnessing their purported energies. Crystals like quartz, believed to vibrate with their own unique frequency, could be arranged in geometric patterns to amplify their mystical powers. Alchemical furnace. In the heart of our laboratory stands the alchemical furnace, stoked to unimaginable temperatures. Here, we'd combine metals and minerals in pursuit of new alloys with strange properties, perhaps even attempting to create materials under high pressure that mimic the conditions deep within the Earth. Celestial alignment. Guided by astrology, we'd conduct our experiments under auspicious celestial events. The alignment of planets and stars might be believed to open a portal to the ether. Understood. Let's focus on the scientific basis for creating exotic matter using actual chemical compounds and materials that we can find or create in a laboratory setting. Here are some of the ways scientists have explored or theorized about creating exotic matter. Bose-Einstein condensates, BECS, are formed when a cloud of atoms is cooled to temperatures near absolute zero. This state of matter is created using laser cooling, where photons from a laser slow down the atoms, reducing their temperature. Superfluid helium. By cooling helium to very low temperatures, it enters a phase known as superfluid helium. This liquid has zero viscosity and can exhibit behaviors like climbing up the walls of its container. Rydberg atoms. In quantum physics, scientists can create Rydberg atoms by exciting electrons to a very high energy level, far from the nucleus. These atoms exhibit an exotic state of matter due to their highly excited electrons. Topological materials. These materials have unique electronic properties due to their topological nature, which remains unchanged even when they are smoothly deformed. Certainly. Let's dive into the fascinating world of condensed matter physics and explore these concepts with both the precision required by an advanced scientist and the simplicity needed to satisfy a curious child's imagination. Bose-Einstein condensates, BECS. Scientific explanation. BECS are formed when a group of bosons, particles like photons, are cooled to temperatures near absolute zero. The mathematics behind BECS involves solving the Gross-Pitaevsky equation, GPE, which is a nonlinear Schrödinger equation that describes the wave function of the condensate. Child's allegory. Imagine you have a bunch of dancers, atoms, all moving to their own rhythm. If the room, the universe, gets really cold, they all start to dance together in perfect harmony, moving as one big wave of dance. Superfluid helium. Scientific explanation. Superfluid helium is helium that has been cooled to a point where it flows without viscosity. It can climb walls and pass through tiny openings without losing any energy. The physics of superfluidity involves understanding quantum mechanics at a macroscopic scale. Child's allegory. Think of superfluid helium like a magical liquid that can flow up and down a playground slide without ever getting tired or slowing down. It's like water that never gets sticky or stuck. Rydberg atoms. Scientific explanation. Rydberg atoms are atoms with one or more electrons in a very high energy state. These electrons are far from the nucleus and have exaggerated responses to electric and magnetic fields. The energy levels of Rydberg atoms are described by the Rydberg formula. Child's allegory. Imagine if you could jump so high on a trampoline that you almost reach the clouds. Topological materials. Scientific explanation. Topological materials have properties that are protected and remain unchanged even when the material is stretched or deformed. Child's allegory. Think of topological materials like Play-Doh. You can squish it, stretch it, or twist it, but it still has the same number of holes or lumps no matter what shape you make. Ultra-high pressure materials. Scientific explanation. These materials are studied under extreme pressures, often found deep within planets. They can have unique properties and phases that only exist under such intense conditions. The study of these materials involves understanding their equations of state and how their atomic structures change under pressure. Child's allegory. Imagine squeezing a sponge really, really hard. The sponge changes shape and might even let out some water. That's like what happens to materials under ultra-high pressure. They change in ways we can't see at normal pressures. Excitons. Scientific explanation. An exciton is a bound state of an electron and an electron hole, a missing electron in a material that can act like a positive particle attracted to each other by the Coulomb force. They are important for understanding the optical properties of materials and are described by quantum mechanical wave functions. Child's allegory. Think of an exciton like a pair of best friends holding hands at a crowded party. One friend is a little negative, the electron, and the other is a little positive, the hole, but together they move through the crowd, the material, as a happy duo. These concepts are the building blocks of modern condensed matter. Certainly. Let's explore the mathematical formulas for each of the concepts we've discussed, and then I'll explain them to an imaginary alien visitor in a way that bridges our worlds. Bose-Einstein condensates Beck's formula. The Gross-Pitaevsky equation GPE is used to describe Beck's, where \psi is the wave function of the condensate, V is the external potential, and G represents the interaction strength. Alien explanation. Imagine a sea of tiny space creatures that, when the cosmic temperature drops, all start to think and move as one collective entity. This unity allows them to flow through the cosmos without losing any individual energy. Superfluid helium. Formula. The Landau's two-fluid model describes superfluid helium, where the total density \rho is the sum of the superfluid \rho_s and normal fluid \rho_n densities. The superfluid has zero viscosity and can flow without friction. Alien explanation. Think of a liquid made of stardust that can glide over any surface of your spacecraft without ever sticking or slowing down, defying the usual cosmic laws of friction. Formula. The energy levels of Rydberg atoms are given by the Rydberg formula. The higher they go, the less energy they need to stay in orbit, just like your ships use less fuel the further they are from a planet's gravity well. Topological materials. Formula. The Hamiltonian for a free exciton in topological materials can be approximated as where h_0 is the unperturbed Hamiltonian, U is the potential energy, E is the elementary charge, \epsilon is the material's dielectric constant, and \math, R_E, \math, R_h are the positions of the electron and hole, respectively. Alien explanation. Envision a material that acts like a cosmic sponge, insulating on the inside but allowing energy to flow freely on its surface, much like how your ship's shields might work, protecting the interior while harnessing energy on the outside. Ultra-high pressure materials. Where P_0, V_0, and K_0 are reference pressure, volume, and bulk modulus, respectively, and K_0 is the pressure derivative of the bulk modulus. Alien explanation. Imagine compressing a piece of your planet until it transforms into a denser form, revealing new and extraordinary properties, much like a star compressing its core to forge new elements. Excitons. Formula. The energy of an exciton can be estimated using where E_text bindu is the binding energy, E is the elementary charge, \epsilon is the dielectric constant, \epsilon_0 is the vacuum permittivity, and R is the average distance between the electron and hole. Alien explanation. Picture two beings from different worlds, bound by an invisible force that allows them to dance together through space, sharing energy without ever touching. These formulas and explanations offer a glimpse into the fascinating physics that governs both our world and the vast universe, potentially including your own extraterrestrial realm. Rydberg atoms. Advanced scientist explanation. Rydberg atoms are highly excited atomic states where one or more electrons are in a high principal quantum number, n. These atoms have exaggerated responses to electric and magnetic fields due to the significant distance of the Rydberg electron from the nucleus, resulting in a weakly bound state with long decay periods. The electron wave functions in Rydberg atoms can, under certain conditions, approximate classical orbits around the nucleus. The energy level spacing in Rydberg atoms decreases with increasing n, leading to a dense Rydberg series converging on the ionization limit. Child's explanation: imagine a Rydberg atom as a tiny solar system. The nucleus is like the sun, and the electrons are like planets. Now, most electrons are close to their sun, but in a Rydberg atom, one electron decides to go on a super long journey far away from the sun. It's so far that it takes a long time to go around, and it can easily be pushed off course by other things flying around in space. Superfluid helium in a spaceship. If superfluid helium were accidentally created inside a spaceship, it would behave quite differently from normal fluids. Superfluid helium has zero viscosity, meaning it flows without any resistance. It could seep through the tiniest cracks and flow along surfaces, defying gravity. It would also conduct heat extremely efficiently, which could lead to unpredictable temperature distributions within the spacecraft. The lack of viscosity means it wouldn't behave as expected under normal fluid dynamics, potentially causing issues with any systems designed to contain or utilize fluids. In a microgravity environment, this could result in the superfluid helium-forming floating blobs that move around the cabin, which could interfere with equipment and instruments. Handling such a situation would require careful containment and removal strategies to avoid damage to the spaceship systems and to ensure the safety of its inhabitants. To an alien engineer from a distant galaxy, I would explain superfluidity as follows. Superfluidity. This is a quantum mechanical phenomenon where a fluid can flow without viscosity, without any internal friction. It occurs at extremely low temperatures, near absolute zero. In this state, the atoms of the fluid form a Bose-Einstein condensate BEC, where they all occupy the same quantum state and behave as a single entity. This allows the superfluid to exhibit remarkable properties, such as flowing through tiny cracks without losing energy, climbing up the walls of containers, and creating vortices that can persist indefinitely. Now, if superfluid helium were to disrupt a spaceship's navigation system, it could cause significant issues. Superfluid helium can flow without resistance and could seep into areas where it's not supposed to be. If it came into contact with the navigation system's components, it could potentially short-circuit the electronics or interfere with the mechanical parts. The lack of viscosity means it could spread rapidly and uncontrollably, affecting sensors and other critical instruments. The navigation system relies on precise measurements and controls, so any disruption by superfluid helium could result in inaccurate readings, loss of control, and potentially jeopardize the spacecraft's mission and safety. It would be crucial to have safeguards in place. Certainly. Let's encapsulate our journey through the realms of theoretical physics and quantum phenomena. Bose-Einstein condensates, BECs. We explored the concept of BECs, which are clusters of atoms cooled to near absolute zero, behaving as a single quantum entity. They are described by the Gross-Pitaevsky equation, a form of the Schrödinger equation tailored for superfluids. Superfluid helium. We discussed superfluid helium, which flows without viscosity and can exhibit behaviors like climbing up container walls. This phenomenon is a macroscopic display of quantum mechanics. Rydberg atoms. We delved into Rydberg atoms, where one or more electrons are in a highly excited state, far from the nucleus, creating exaggerated responses to external fields. Topological materials. We touched on topological materials, which have unique electronic properties that remain unchanged even when the material is deformed, thanks to their topological nature. Ultra-high pressure materials. We considered materials under extreme pressures, which can exhibit unique properties and phases, potentially leading to the creation of exotic matter. Excitons. We examined excitons, which are pairs of electrons and holes bound together, playing a crucial role in the optical properties of materials. Superfluidity in space. We imagine the implications of superfluid helium aboard a spacecraft, noting its potential to disrupt navigation systems due to its lack of viscosity and ability to flow through tiny spaces. To future readers and watchers, this summary encapsulates a thought experiment that blends the boundaries of current scientific understanding with the imaginative possibilities of theoretical physics. It's a testament to human curiosity and our relentless pursuit to understand the universe around us. Whether you're a seasoned scientist or a curious learner, may this serve as a springboard for your own explorations into the wonders of physics.